Every science textbook you have ever read lied to you about the solar system. Those neat little diagrams with the planets lined up like marbles. They are not simplifications. They are lies. Because if you shrink the sun down to the size of a basketball and set it on a sidewalk in New York, the Earth becomes a grain of sand 15 meters away. Neptune sits 5 blocks down the street. And the actual edge of the solar system, the real edge, is halfway to San Francisco. In 2024, a spacecraft flying through the darkness beyond Pluto discovered something that nobody expected. The solar system does not end where we thought it did. It keeps going, and what lies beyond is so vast that the fastest thing humanity has ever built will take 30,000 years to cross it. Tonight, we are going to travel from the surface of this planet to the outermost edge of the sun's domain. And by the end, you will understand why everything you were taught about the size of our solar system was wrong. If you enjoy our calm nighttime journeys, remember to like and subscribe. We highly encourage our community to discuss the video topics in the comments and react to other comments. It is the most fun when we share our thoughts. Now, let us begin. Tonight, we are going on the longest journey this channel has ever attempted. We are going to travel from the surface of this planet to the outermost edge of the sun's domain. Along the way, we will pass through hidden oceans buried beneath moons of ice. We will watch 2 spacecraft die in the silence of interstellar space, their plutonium hearts fading after nearly 50 years. We will stand at the edge of the largest structure in the solar system, a ghost shell of trillions of frozen objects that no telescope has ever photographed. And by the time we reach the end, you will understand something that most people, including most scientists, have been getting wrong for decades. The solar system is not the size you were taught. It is not even close. Chapter 1. The Lie in Your Textbook. Open any science textbook printed in the last 50 years and find the diagram of the solar system. You have seen it 1,000 times. The sun sits in the center, a yellow circle. Around it, the planets are arranged in a neat row. Mercury, Venus, Earth, Mars, then a little gap for the asteroid belt, then Jupiter, Saturn, Uranus, Neptune. Sometimes Pluto is there at the end. The planets are shown as roughly evenly spaced marbles. Maybe the outer ones are a bit farther apart, but the overall impression is tidy, compact, knowable. A neighborhood you could stroll through on a Sunday afternoon. That diagram is a lie, not a simplification, not an approximation, a lie. And once you understand how badly it distorts reality, you will never look at the night sky the same way again. Let us start with a simple exercise. Let us shrink the sun down to the size of a basketball and place it on the sidewalk in New York City. In this model, at a scale of 1 to 10 billion, the sun is a ball about 14 centimeters across. You can hold it in your hands. Now, where is Earth? Earth in this model is a tiny pinhead, a sphere barely 1 millimeter across, and it sits about 15 meters away from the basketball. That is roughly the width of a 4-lane road. Already the distance feels wrong. The sun is a basketball and the Earth is a grain of sand across the street. But keep walking. Mars is 23 meters from the sun. Jupiter is 78 meters away. Saturn is 143 meters. Uranus is 287 meters. And Neptune, the last official planet, is 450 meters from the sun. That is nearly half a kilometer. You started with a basketball on a sidewalk, and now you are standing 5 blocks away, looking back, and you cannot even see the basketball anymore. The planets, all 8 of them, are invisible specks, scattered along those blocks, separated by absolutely nothing. Empty sidewalk, empty air, nothing. And that is just a Neptune. That is just the planetary solar system. The Kuiper Belt, the icy ring of debris beyond Neptune, stretches to roughly 750 meters in this model. And the Oort Cloud, the true outer boundary of the Sun's gravitational domain, extends in this model from dozens of kilometers to hundreds of kilometers away. In a model where the Sun is a basketball on a New York sidewalk, the edge of the solar system is roughly halfway to San Francisco. There is a website called If the Moon Were Only 1 Pixel. It was built by a designer named Josh Worth, and it presents the solar system to scale in your web browser. You scroll sideways, you pass the Sun, a circle of pixels. Then you scroll and scroll and scroll through blackness, empty space, nothing. Minutes of scrolling before you reach the next planet. And between the planets, in the dead black emptiness, the site leaves you messages. Most of space is just space, it says. That sentence alone should keep you up at night. Now here is the part that makes this personal. Every diagram you ever saw in school made you feel like the solar system was something manageable, something you could wrap your mind around. It gave you the false impression that the planets are neighbors, that Mars is right next door, that Saturn is a short trip away, that the edge of the solar system is somewhere out there, not too far, reachable. And that is wrong. The distances between the planets are so vast that they defy human intuition. The emptiness between them is so total that it constitutes the overwhelming majority of what the solar system actually is. The solar system is not a collection of planets. It is a collection of nothing, with a few specks of matter scattered through it at absurd intervals. And in 2024, we learned that the nothing is even bigger than we thought. A spacecraft called New Horizons has been flying through the outer solar system since 2006. It is the craft that gave us our first close look at Pluto in 2015. After Pluto, it kept going deeper into the Kuiper Belt, eventually flying past a strange snowman-shaped object called Arakoth in 2019. And as it flew, an instrument on board called the Venetia-Burney Student Dust Counter kept measuring the amount of dust in its path. Dust in the outer solar system comes from collisions between Kuiper Belt objects. The more objects there are, the more dust there should be. Every model predicted that as New Horizons passed beyond 50 astronomical units from the Sun, the dust levels should decline. The Kuiper Belt was supposed to end around there. The objects were supposed to thin out. The dust was supposed to fade. It did not fade. Between 45 and 55 astronomical units, the dust levels increased. They went up, not down. The readings defied every model. Something was out there, beyond the supposed edge of the Kuiper Belt, producing collisions, generating dust, populating a region of space that was supposed to be empty. Alan Stern, the principal investigator for New Horizons, said these new scientific results may be the first time that any spacecraft has discovered a new population of bodies in our solar system. Ground-based observations using the Subaru telescope in Hawaii confirmed the finding. Kuiper Belt objects were being discovered at distances of nearly 90 astronomical units, far beyond the classical edge at 50. The Kuiper Belt does not end where the textbooks say it ends. It may extend to 80 astronomical units or beyond. There may even be a second belt entirely, a whole additional ring of icy debris that nobody knew was there. The solar system just got bigger, again. And this raises a question that sounds simple but has no simple answer. How big is the solar system? What counts as the solar system? Is it the distance to the last planet? That would be 30 astronomical units. The orbit of Neptune. Is it the Kuiper Belt? That used to be 50 astronomical units, but now might be 80 or 90. Is it the heliopause, the boundary where the Sun's solar wind meets the interstellar medium? That is roughly 120 astronomical units. Is it the Oort Cloud, the vast spherical shell of icy objects that surrounds everything? That extends to 100,000 astronomical units, perhaps 200,000. Or is it the full reach of the Sun's gravitational influence? That stretches roughly 2 light-years in every direction. Depending on which definition you use, the solar system is either 60 astronomical units across or 400,000 astronomical units across. That is a difference of nearly 7,000 times. It is like asking how big is your house and getting answers that range from the kitchen to the entire state. Tonight, we are going to travel from the surface of this planet to the outermost edge of the sun's domain. And by the time we get there, you will understand why most people have been dramatically underestimating how big our home really is. But before we go outward, we need to understand why even the distances inside the solar system, the ones between the planets you learned about in school, are enough to make human travel functionally impossible. The first step on this journey is the moon. It looks close. It is not. Chapter 2. The inner solar system is already too big. 384,400 kilometers. That is the distance from the surface of the Earth to the surface of the moon. Written out, it does not look like much. A number you can say in a single breath, but let us feel it. Line up 30 Earths in a row, edge to edge, like beads on a string. That is the gap between here and the moon. 30 entire planets. The Apollo astronauts crossed that distance in 3 days. 3 days inside a capsule the size of a car, hurtling through a vacuum at speeds that would kill you instantly if anything went wrong. And the moon is the closest thing to us in the entire universe. It is the first step on the staircase, and it already takes 3 days at rocket speed. If you drove a car to the moon at highway speed, roughly 100 kilometers per hour, the trip would take about 5 months. If you walked 8 hours a day, it would take roughly 9 years. 9 years of walking to reach the nearest object in space. And here is the detail that matters for everything that comes next. At the distance of the moon, the speed of light starts to become a problem. Light travels at roughly 300,000 kilometers per second. At the moon's distance, that means a signal takes 1.3 seconds to get there. You say hello to an astronaut on the moon, and their reply arrives 2.6 seconds later. That is manageable. That is a conversation with a slight delay, like a bad video call. But the moon is the last place in the solar system where that kind of communication is possible. After the moon, the lag grows, and it never stops growing. Mars is next door. In solar system terms, Mars is the house across the street, and Mars will break your heart. At its closest approach, when Earth and Mars are on the same side of the Sun, the distance between them is roughly 55 million kilometers. At its farthest, when the Sun sits between them, the gap stretches to over 400 million kilometers. The average distance is about 225 million kilometers. At that average distance, light takes 12.5 minutes to make the trip. One way. A signal from Earth to the Curiosity rover takes between 3 and 22 minutes, depending on where the planets are in their orbits. If something goes wrong with the rover, by the time the distress signal reaches Earth, the event has already been over for minutes. By the time a corrective command arrives back at Mars, nearly 3/4 of an hour may have passed. There is no real-time communication with Mars. There are no phone calls, no video chats, no emergency instructions. There is only waiting. In 2014, the Curiosity rover turned its camera toward the sky and photographed Earth. Everything you have ever known, every person alive, every city, every forest, every ocean, reduced to a faint bluish smudge in an alien sky. A dot. That is what we look like from the planet next door. That photograph is one of the most important images ever taken, not because it is beautiful, though it is, because it tells you the truth about where you live. You live on a speck, surrounded by distances so large that even light takes minutes to cross them. And Mars is close. Now consider what it takes to actually get there. The Parker Solar Probe, at its closest pass to the Sun, reaches speeds of roughly 635,000 kilometers per hour. It is the fastest object humanity has ever built. At that speed, you could fly from New York to Los Angeles in about 20 seconds. At that speed, you could reach Mars at closest approach in roughly 3.5 days. But no crewed spacecraft can travel that fast. The Parker Solar Probe achieves its speed by falling toward the Sun, trading gravitational potential energy for velocity. A crewed mission to Mars cannot do that. Realistic travel times for astronauts heading to Mars are 6 to 9 months each way. 6 to 9 months in a metal tube exposed to cosmic radiation, with no possibility of resupply, no possibility of rescue, and no possibility of a real-time conversation with anyone on Earth. And that is the trip to our nearest planetary neighbor. Beyond Mars lies the asteroid belt. And here is where the movies have been lying to you for decades. Every science fiction film shows the asteroid belt as a dense field of tumbling rocks, a cosmic obstacle course where spacecraft dodge and weave between boulders. Han Solo threading the Millennium Falcon through a hail of stone. It looks thrilling. The reality is the exact opposite. The asteroid belt spans from roughly 2.2 to 3.2 astronomical units from the Sun. It contains millions of objects. But the average distance between any two asteroids is approximately 1 million kilometers. 1 million kilometers of nothing between each rock. You could fly straight through the asteroid belt, eyes closed, engines off, and the odds of hitting anything are astronomically small. NASA has done exactly this. Multiple spacecraft have passed through the belt without even attempting evasive maneuvers. Not because the pilots were brave, because there was nothing to dodge. The entire mass of the asteroid belt, all the millions of objects combined, adds up to roughly 4% of the mass of the Moon. 4%. The asteroid belt is not a wall. It is not a barrier. It is a desert with a few scattered grains of sand separated by gulfs of empty space. But it marks a psychological boundary. Beyond the belt, you leave the rocky inner planets behind. You enter the realm of the gas giants, and the distances are about to stop being large and start being absurd. The inner solar system, everything from the Sun to the asteroid belt, spans roughly 3.5 astronomical units. That is about 525 million kilometers, already an incomprehensible distance. But the inner solar system is the front porch, the part of the solar system that most people have never thought about. The part beyond the asteroid belt is where the true scale begins to reveal itself. Jupiter sits at 5.2 astronomical units from the Sun. That is 5.2 times the distance between the Earth and the Sun. Light takes between 33 and 54 minutes to travel between Earth and Jupiter, depending on orbital positions. Saturn is at 9.5 astronomical units, Uranus at 19.2, Neptune at 30. Every step outward roughly doubles the distance of the last. The gaps between planets grow exponentially, and with each step, communication becomes harder, travel times become longer, and the isolation becomes more complete. Jupiter, the largest planet in the solar system, the gravitational king, holds secrets in its moons that could rewrite the story of life itself. Because beneath the ice of one tiny moon, there is an ocean containing 2 to 3 times more water than all the oceans on Earth combined. And right now, a spacecraft the size of a basketball court is crossing the solar system to search for signs of life in that ocean. It left Earth in October of 2024. It will not arrive until 2030. 6 years of flying through nothing to reach a moon where something extraordinary might be hiding beneath the ice. Chapter 3: Oceans in the Dark. Europa is a moon of Jupiter. It is slightly smaller than our own moon. Its surface is a shell of ice, cracked and crosshatched with reddish-brown lines that stretch for thousands of kilometers. It looks like a cracked egg. And beneath that shell, buried under 15 to 25 kilometers of ice, is a global saltwater ocean that contains 2 to 3 times more water than all the oceans on Earth combined. Think about that. A moon smaller than ours, orbiting a gas giant nearly 800 million kilometers away, hiding more water than every drop on our entire planet. The Atlantic, the Pacific, the Indian Ocean, the Arctic, all of them combined and then doubled. That is Europa's ocean. And it has been there, churning in the dark, for billions of years. On October 14th, 2024, NASA launched the Europa Clipper. It is the largest spacecraft the agency has ever built for a planetary mission. When its solar arrays and antennas are fully deployed, it stretches over 30 meters across. It carries 9 scientific instruments and a gravity experiment. It is designed to answer one question: could Europa support life? The spacecraft will not arrive at Jupiter until April of 2030, nearly 6 years of travel. Along the way, it used Mars for a gravity assist in March of 2025, successfully testing its ice-penetrating radar instrument called RESON by bouncing signals off the Martian surface. In December of 2026, it will swing past Earth for a second gravity assist before making the long final leg to Jupiter. Once there, it will not orbit Europa directly. Jupiter's radiation belts would fry its electronics within weeks. Instead, it will orbit Jupiter on long looping paths that bring it close to Europa 49 times, some passes as low as 26 kilometers above the surface. Close enough that if you were standing on Europa, the spacecraft would fill a significant portion of your sky. The radar will peer beneath the ice. Spectrometers will analyze the surface chemistry. A thermal instrument will map heat signatures that could indicate where the ocean meets the ice from below. The mission is the most ambitious hunt for extraterrestrial life since we began exploring Mars. But even as Europa Clipper was being launched, the scientific picture was getting more complicated. In December of 2025, a study published in Nature Astronomy using data from the Juno spacecraft suggested that Europa's ice shell may be thicker than scientists had hoped, potentially reducing the interaction between the ocean and the surface. If the ice is too thick, nutrients from the surface may never reach the water below. An ocean with water but no chemistry is just a dark, cold tank. Then, in January of 2026, Paul Byrne of Washington University in St. Louis published a study in Nature Communications arguing that Europa's seafloor may be geologically quiet. The tidal heating that was supposed to drive hydrothermal vents on the ocean floor, the same kind of vents that support entire ecosystems in the deep oceans of Earth, may not be strong enough. The energy just does not seem to be there to support life, at least today, Byrne wrote. If the seafloor is cold and dead, there may be no energy source to power biology in the ocean above. But in that same month, another team of researchers offered a counterpoint. They found that salty, nutrient-rich ice on Europa's surface can become heavy enough to break free and sink through the ice shell, potentially carrying life-supporting chemicals down into the ocean. The ice itself might be delivering the ingredients, not from the bottom up through volcanic vents, from the top down through dense sinking ice. The debate is wide open. We do not know if Europa is alive. We do not know if its ocean is a cradle or a coffin. That is why Europa Clipper exists. And Europa is not the only ocean world in the outer solar system. Saturn's moon Titan is the only moon in the solar system with a thick atmosphere. Methane rain falls from its orange sky. Lakes of liquid hydrocarbons pool on its surface, reflecting the faint light of a sun that is barely more than a bright star at that distance. For years, scientists believed Titan harbored a global subsurface water ocean beneath its icy crust. But in December of 2025, a study published in Nature reanalyzed data from the Cassini spacecraft and delivered a blow. Titan's interior may not contain a global liquid ocean at all. Instead, it appears to be more of an icy slush with only scattered pockets of liquid. Not the vast hidden sea scientists had imagined. NASA has a mission going there too. Dragonfly is a rotorcraft, an 8-rotor drone that will fly through Titan's thick atmosphere, hopping from site to site, sampling the surface chemistry. It carries a seismometer to listen to Titan's interior. It is scheduled to arrive in 2034, nearly a decade from now. Then there is Enceladus, Saturn's tiny moon, only about 500 kilometers across, that shocked the world when the Cassini spacecraft flew through geysers of water ice erupting from its south pole. Enceladus is shooting its ocean into space. Cassini flew through those plumes and tasted them. It found water, salt, silica, molecular hydrogen, and complex organic molecules. Everything a microbe could want. Enceladus may be the most promising place to look for life in the entire solar system. And there is no approved mission to go there, not one. The solar system's most tantalizing target sits at 9.5 astronomical units from the Sun, behind a moat of emptiness so vast that simply reaching it requires years of planning and billions of dollars. This is the cruel mathematics of the outer solar system. The most exciting places, the places where life might actually exist right now, are so far away that visiting them requires decade-long missions and spacecraft that cost more than many countries' entire annual budgets. Europa is at 5.2 astronomical units. Light takes up to 52 minutes to reach it. A spacecraft takes 6 years. Enceladus is even farther. The distance is not just inconvenient. It is a prison wall. It separates us from answers that could change everything we understand about biology, about the universe, about whether we are alone. And these ocean worlds, as extraordinary as they are, still exist within what astronomers call the inner solar system, the region where the sun's light is at least dimly visible, the region where the planets are gravitationally tidy, following well-understood orbits. Beyond Neptune, beyond the last planet, the solar system enters a region so vast and so empty that the sun itself begins to look like just another star. And in 2024, a spacecraft already out there, farther from the sun than Pluto ever gets, discovered something that nobody expected. The solar system does not end where we thought it did. It keeps going, and what lies beyond is bigger than everything we have discussed so far combined. Chapter 4. Beyond the last planet. Neptune orbits the Sun at 30 astronomical units. That means it is 30 times farther from the Sun than the Earth is. Light takes over 4 hours to reach it. The Voyager 2 spacecraft, the only human-made object to ever visit Neptune, took 12 years to get there. Neptune is the last planet. Beyond it, the solar system becomes something else entirely. It stops being a neat arrangement of worlds and becomes a frontier. The Kuiper Belt begins at Neptune's orbit and stretches outward into the darkness. It is a vast ring of icy debris, the frozen leftovers from the formation of the solar system 4.5 billion years ago. Pluto is the most famous Kuiper Belt object, but it is just one among thousands. Eris, slightly more massive than Pluto, orbits even farther out. Makemake, Haumea, Quaoar, Sedna, each a small frozen world drifting through a silence so deep it is almost unimaginable. Pluto's average distance from the Sun is 39 astronomical units. At its farthest point, it swings out to 49. When New Horizons reached Pluto in July of 2015, after a journey of 9.5 years, it revealed a world that nobody expected. Mountains of water ice, some rising 3.5 kilometers above the surface. A vast heart-shaped glacier of frozen nitrogen called Sputnik Planitia, 1,000 kilometers across, slowly flowing like a glacier on Earth, but made of nitrogen ice instead of water ice. A thin haze of atmosphere, blue when backlit by the sun. Pluto was not a dead frozen ball. It was a complex geologically active world, with more going on than anyone had predicted. After Pluto, New Horizons kept flying. On January 1st, 2019, it reached a Kuiper Belt object called Arakoth. Formerly known by its technical designation 2014, MU69. Arakoth turned out to be a contact binary, 2 rounded lobes pressed gently together like a snowman. It is the most distant object ever explored up close by a human spacecraft. It is small, roughly 35 kilometers long. It is ancient, likely unchanged since the earliest days of the solar system, and it is utterly alone, drifting in a void so empty that the nearest known neighbor is millions of kilometers away. But it was what New Horizons found after Arakoth that changed the conversation about the solar system's size. The Venetia Burney Student Dust Counter, an instrument designed and built by students at the University of Colorado Boulder, had been measuring dust levels throughout the entire mission. As New Horizons passed beyond 45 astronomical units, the models predicted that dust levels should decline. The spacecraft was supposed to be leaving the Kuiper Belt behind. The icy objects were supposed to be thinning out. The collisions that produced dust were supposed to be getting rarer. Instead, between 45 and 55 astronomical units, dust levels went up. The instrument recorded higher fluxes than expected, not lower. Something was out there, populating a region of space that was supposed to be empty, generating collisions, producing debris. The findings were published in the Astrophysical Journal Letters in February of 2024. At the same time, ground-based observers using the Subaru telescope in Hawaii were discovering Kuiper Belt objects at distances far beyond the supposed outer edge. Objects were being found at nearly 90 astronomical units, almost twice the distance of the classical Kuiper Belt boundary at 50. The implications were staggering. Either the Kuiper Belt extends far beyond what anyone calculated, reaching out to 80 astronomical units or more, or there is a second belt entirely, a whole additional population of icy objects orbiting in a ring that no one knew existed until a student-built instrument on a spacecraft that almost nobody was paying attention to anymore picked up the signal. Alan Stern, the principal investigator for New Horizons, said that these findings may represent the first time any spacecraft has discovered a new population of bodies in our solar system. New Horizons is expected to have enough power and propellant to operate through the 2040s, at distances beyond 100 astronomical units. If the spacecraft survives that long, it could potentially detect the transition from Kuiper Belt dust to interstellar dust, the point where the material from our solar system gives way to material from other stars. We do not know where that boundary is. We have never measured it directly. And there is one more object worth mentioning in this chapter, because it tells us something about what lurks in the even deeper darkness beyond the Kuiper Belt. In 2014, astronomers discovered a comet. Its designation is C2014 UN-271, but it is better known as Comet Bernardinelli-Bernstein, named after the two researchers who identified it. It is the largest Oort Cloud comet ever found. Its nucleus is approximately 140 kilometers across. That is more than 10 times the size of most known comets. It is a mountain of ice, a frozen relic from the outermost edges of the solar system, falling slowly inward on an orbit that takes millions of years to complete. In June of 2025, the Atacama Large Millimeter Array, known as ALMA, detected molecular carbon monoxide outgassing from Comet Bernardinelli-Bernstein at a distance of 16.6 astronomical units from the Sun. That was the first direct detection of molecular activity from a comet at such a great distance. The comet was already active, already venting gas, even though it was still far beyond Saturn's orbit. This object began its journey from the Oort Cloud thousands or perhaps millions of years ago. It is a messenger, a frozen ambassador from the outermost edges of the Sun's domain. And it is enormous. The Kuiper Belt, even in its newly extended form, is still relatively close to the Sun in cosmic terms. It exists between 30 and perhaps 90 astronomical units. But beyond it lies a region so vast that it dwarfs everything we have discussed so far. A spherical shell of trillions of icy objects, stretching out to 100,000 astronomical units or more. A region so large that it extends a quarter of the way to the nearest star. And we have never seen it. We have never photographed a single object in it. We know it exists only because of the comets it occasionally throws at us, like messages in bottles from the deep. It is the largest structure in the solar system by far, and it is completely invisible. That structure has a name, and it is where we are going next. Chapter 5: The Ghost Shell. In 1950, a Dutch astronomer named Jan Oort was studying the orbits of long-period comets. These are comets that take thousands or even millions of years to complete a single orbit around the Sun. They come from every direction, not just from the flat plane where the planets orbit. They arrive from above, below, sideways, at angles that make no geometric sense if you assume they originate in the Kuiper Belt, which is a flat disk. Oort realized that these comets must be coming from somewhere else, somewhere spherical, somewhere enormous. He proposed that the solar system is surrounded by a vast shell of icy objects, a cloud of trillions of frozen bodies extending far beyond the planets, far beyond the Kuiper Belt, reaching out to the very edge of the Sun's gravitational influence. He was building on earlier work by the Estonian astronomer Ernst Öpik, who had proposed a similar idea in 1932. The structure became known as the Oort Cloud. The numbers are difficult to comprehend. The inner edge of the Oort Cloud begins at roughly 2,000 astronomical units from the Sun. The outer edge extends to 100,000 astronomical units, possibly 200,000. At 100,000 astronomical units, the Oort Cloud reaches approximately 1.6 light-years from the Sun. The nearest star, Proxima Centauri, is 4.24 light-years away. The Oort Cloud extends roughly 40% of the way there. Let that settle for a moment. The solar system, if you define it by the Oort Cloud, is not a small disk around a star. It is a sphere approximately 3 light-years in diameter. 3 light-years. Light, the fastest thing in the universe, takes 3 years to cross it. And this is not empty space. This is space filled, however sparsely, with trillions of frozen objects, each one a remnant of the solar system's formation, each one orbiting the Sun so slowly and at such tremendous distances that they exist in near-perfect darkness and near absolute cold. The objects in the Oort Cloud are too small, too dark, and too far away to be seen with any telescope ever built. No object in the Oort Cloud has ever been directly observed. Not one. We know the Oort Cloud exists because of the comets it sends inward, long-period comets whose orbital trajectories, when traced backward, point to this distant shell. Occasionally, a passing star or a tidal force from the galaxy itself nudges one of these objects out of its ancient orbit and sends it falling toward the Sun. It takes millions of years to arrive. When it does, it blooms briefly into a comet with a tail, makes a single screaming pass around the Sun, and then either swings back out into the deep or is destroyed. There may be objects in the Oort Cloud that we have partially glimpsed. Sedna, discovered in 2003, has one of the most extreme orbits of any known solar system body. At its closest approach to the Sun, Sedna comes to about 76 astronomical units. At its farthest, it swings out to roughly 900 astronomical units. Its orbital period is over 11,000 years. Sedna spends most of its life in absolute darkness and silence, so far from the Sun that our star is barely distinguishable from the other stars in the sky. It is considered an inner Oort Cloud candidate, a body that orbits in the transition zone between the Kuiper Belt and the true Oort Cloud. Another object, designated 2012 VP 113, follows a similar pattern. Discovered in 2012, it never comes closer than 80 astronomical units. These objects are loners, drifting through a no-man's land between the known solar system and the ghost shell beyond. In 2025, a research paper suggested that the inner Oort Cloud, sometimes called the Hills Cloud, may have a spiral structure rather than the simple donut shape scientists had assumed. If true, the architecture of the Oort Cloud is even more complex than we imagined. A spiraling galaxy of ice surrounding the Sun, invisible, immense, and entirely unmapped. And here is the fact that makes the Oort Cloud truly terrifying in terms of scale. Voyager 1, the most distant human-made object, is currently at roughly 166 astronomical units from the Sun. It has been traveling for nearly 49 years. It is moving at approximately 61,200 kilometers per hour, and the inner edge of the Oort Cloud begins at 2,000 astronomical units. Voyager will not reach the inner edge of the Oort Cloud for another 300 years. 300 years of flight at 61,000 kilometers per hour, just to touch the beginning of the ghost shell. And the outer edge? Voyager will not pass through the outer Oort Cloud for another 30,000 years. 30,000 years. That is longer than all of recorded human history. The cave paintings at Lascaux in France are roughly 17,000 years old. They are among the oldest surviving artworks made by human hands. By the time Voyager exits the Oort Cloud, assuming it survives that long as a dead, unpowered piece of metal drifting through the void, human civilization will be unrecognizable, or it will be gone entirely. The Oort Cloud is the solar system's true frontier. No human technology currently planned or even seriously proposed will ever explore it. It is too far, too vast, too empty. The distances are simply too large for any propulsion system we can currently envision. And yet the Oort Cloud is part of our solar system. It belongs to the Sun. Every frozen body in it is gravitationally bound to the Sun, orbiting slowly, patiently, in the dark. The solar system is not 30 astronomical units across. It is not 50. It is not 90. It is potentially 200,000 astronomical units across, a sphere stretching 3 light-years in diameter, containing trillions of invisible objects surrounding us in every direction. And right now, for the first time, we are about to map the boundary between the Sun's influence and the rest of the galaxy. Because in September of 2025, NASA launched a spacecraft specifically designed to answer one question. Where does our solar system actually end? And what does the wall look like? Chapter 6. The Wall of Fire. The Sun is not just a ball of light, it is an engine. Every second, it converts roughly 620 million metric tons of hydrogen into helium through nuclear fusion. The energy released in that process radiates outward as light and heat. But the Sun also produces something else, a wind. The solar wind is a continuous stream of charged particles, mostly protons and electrons, flowing outward from the Sun's corona at speeds between 350 and 750 kilometers per second. This wind does not stop at the planets. It does not stop at the Kuiper Belt. It flows outward for billions of kilometers, carrying the Sun's magnetic field with it, inflating a vast bubble around the entire solar system. That bubble is called the heliosphere. Inside the heliosphere, the Sun's magnetic field dominates. It is the Sun's territory, the Sun's electromagnetic kingdom. Outside the heliosphere, you are in interstellar space, the galaxy's territory, a different regime entirely, dominated by the magnetic fields and charged particles of other stars and the general interstellar medium. The boundary between the two is called the heliopause. It sits at roughly 120 astronomical units from the Sun, though its exact position varies depending on the Sun's activity and the pressure of the interstellar medium pushing against it. The heliosphere is not a perfect sphere. The Sun is moving through the galaxy at roughly 230 kilometers per second. This motion compresses the heliosphere on the leading edge, the side facing the direction the Sun is traveling, and stretches it out behind, creating a shape more like a windsock or a comet tail than a ball. The front of the heliosphere is pushed inward. The tail streams behind. The bubble breathes with the Sun's 11-year activity cycle, expanding and contracting as the solar wind strengthens and weakens. And for the first time, we now have a spacecraft designed specifically to map this boundary in detail. On September 24, 2025, NASA launched the Interstellar Mapping and Acceleration Probe, known as IMAP, aboard a SpaceX Falcon 9 rocket from Kennedy Space Center. IMAP traveled to Lagrange Point 1, a gravitationally stable spot roughly 1.5 million kilometers from Earth in the direction of the Sun, where it arrived on January 10, 2026. Its 2-year primary science mission officially began on February 1, 2026. IMAP carries 10 scientific instruments, including 3 energetic neutral atom detectors with 15 to 35 times greater sensitivity than its predecessor mission, IBEX, the Interstellar Boundary Explorer. These instruments detect energetic neutral atoms, particles that are created when charged particles from the solar wind interact with the interstellar medium at the heliosphere's edge. These neutral atoms fly in straight lines back toward Earth, unaffected by magnetic fields, carrying information about the conditions at the boundary. By collecting these atoms, IMAP can construct maps of the heliosphere's edge, the same way you might photograph a distant wall by catching the light bouncing off it. David McComas, a professor at Princeton University and the principal investigator for IMAP, leads the mission with an international team of 27 partner institutions. The mission will answer questions that have been nagging heliophysicists for decades. What shape is the heliosphere? Does it breathe with the solar cycle? How does it protect us from galactic cosmic rays? How did it shape conditions for life on Earth? That last question is not rhetorical. Research has suggested that up to 3 million years ago, the heliosphere may have shrunk dramatically. Increased pressure from the interstellar medium, the material between stars, may have compressed the Sun's bubble so severely that its boundary retreated to inside the orbit of the Earth. For a period, our planet may have been exposed directly to the interstellar medium, bathed in galactic cosmic rays, with no magnetic shield to deflect them. This timing coincides with known climate shifts and potentially with milestones in human evolution. Merv Ofer, a heliophysicist who has studied this scenario, raised a profound question. If we were at times outside of the heliosphere, how did life evolve on Earth? It is really critical for us to understand which type of radiation Earth would have encountered. The heliosphere is not just an abstract boundary on a chart, it is a shield. It is the reason cosmic radiation levels on Earth are manageable. Without it, the surface of this planet would be bombarded by high-energy particles from across the galaxy. The heliosphere's existence may be one of the reasons complex life was able to evolve here at all. IMAP will produce the most detailed maps of this shield ever created. It will tell us where the boundary is, how it moves, what it looks like from the inside. And it will do this from a vantage point less than 2% of the way to the boundary itself. IMAP is stationed at 1.5 million kilometers from Earth. The heliopause is at roughly 18 billion kilometers. IMAP is mapping a wall it will never visit, using the faint atomic messengers that drift back from the edge. The heliosphere sits at roughly 120 astronomical units, the edge of the Sun's electromagnetic influence. But only 2 human-made objects have ever crossed that boundary. And right now, in 2026, both of them are dying. Their plutonium hearts are fading. Their instruments are being shut down one by one. They are the most distant objects humanity has ever created. They carry our music, our greetings, our photographs, and they are about to go silent forever. Chapter 7. The Dying Explorers. On September 5, 1977, a spacecraft left Earth. It weighed roughly 825 kilograms. It carried 10 scientific instruments, a 3.7-meter high-gain antenna, 3 radioisotope thermoelectric generators powered by the decay of plutonium-238, and a golden record. Its name was Voyager 1. It is now roughly 166 astronomical units from Earth. That is more than 25 billion kilometers. It is the most distant human-made object in existence. Nothing we have ever built has traveled farther. And in late 2026, Voyager 1 will reach a milestone that captures the scale of the solar system more viscerally than any number. It will be one light day from Earth. That means a signal traveling at the speed of light, the fastest speed possible in the universe, will take 24 hours to reach the spacecraft. One full day. And 24 hours to come back. Suzanne Dodd, the Voyager project manager at the Jet Propulsion Laboratory, described what this means for communication. If I send a command and say, "Good morning, Voyager 1 at 8 a.m. on a Monday morning," I am going to get Voyager 1's response back to me on Wednesday morning at approximately 8 a.m. A 2-day round trip for a single hello, and the distance is growing every second. Voyager 1 is moving away from the Sun at roughly 61,200 kilometers per hour. It will never stop. It will never slow down. There is nothing out there to slow it down. It will drift through interstellar space for millions of years. A dead, silent artifact, carrying a golden record that nobody will ever play. Both Voyager spacecraft, Voyager 1 and Voyager 2, rely on plutonium-238 radioisotope thermoelectric generators for power. The plutonium decays. The decay produces heat. The heat is converted to electricity. But plutonium-238 has a half-life of 87.7 years. Each year, the generators produce roughly 4 fewer watts of power. When the spacecraft launched, they generated about 470 watts each. Now they produce far less. And the instruments, the computers, the heaters, the communication systems, all need electricity to function. In March of 2025, NASA turned off the cosmic ray subsystem on Voyager 1 and the low-energy charged particle instrument on Voyager 2. 3 science instruments remained on each spacecraft, but the plan is already set. In 2026, Voyager 1's low-energy charged particle instrument will be shut down, and Voyager 2's cosmic ray subsystem will follow. Each spacecraft will be left with 2 instruments: the magnetometer, which measures the magnetic field of interstellar space, and the plasma wave subsystem, which detects waves and vibrations in the charged particles around the spacecraft. 2 instruments each, running on fading power, measuring the properties of a region of space that no other human technology has ever reached. Linda Spilker, the Voyager project scientist at JPL, said every minute of every day, the Voyagers explore a region where no spacecraft has gone before. That also means every day could be our last. But that day could also bring another interstellar revelation. So we are pulling out all the stops, doing what we can to make sure Voyagers 1 and 2 continue their trailblazing for the maximum time possible. Engineers hope to keep at least 1 instrument running on each probe into the early 2030s. After that, the power will be too low. The last instrument will be turned off. The last command will be sent. The last signal will go dark. And the 2 spacecraft will continue drifting, unpowered, silent, through interstellar space for eternity, or at least for a very long time. Each Voyager carries a golden record. It is a 12-inch gold-plated copper phonograph record, enclosed in a protective aluminum jacket. On the cover, instructions are engraved for any intelligent being who might find it, explaining how to play the record and where it came from. On the record itself are 115 images encoded as audio signals, greetings in 55 human languages, 27 pieces of music, from Bach to Chuck Berry to Javanese gamelan, and sounds of Earth. Wind, rain, surf, birdsong, a human heartbeat. The record was the creation of a committee chaired by Carl Sagan. It was designed as a message in a bottle, cast into the cosmic ocean by a species that knew it might never be answered. And it almost certainly will never be answered. The nearest star that Voyager 1 will pass close to is a dim red dwarf called AC plus 793888 in the constellation Camelopardalis. Voyager will come within 1.6 light-years of that star in approximately 40,000 years. It will not be captured by the star's gravity. It will not enter orbit. It will drift past, silently, in the dark, and continue into the galaxy. The golden record will outlast every building on Earth. It will outlast every city, every nation, every language, every religion. It will outlast the sun itself. In 5 billion years, when the sun has swollen into a red giant and consumed the inner planets, the Voyager spacecraft will still be out there, somewhere in the galaxy, carrying the record. The copper will not corrode in the vacuum of space. The engravings will not fade. The record will persist, unplayed, unheard, for billions of years. And here is the detail that ties this chapter to the larger story of the solar system's size. Voyager 1 crossed the heliopause in August of 2012. It left the heliosphere. By one definition, it left the solar system. But by another definition, the gravitational one, it has not even begun to leave. The Oort Cloud stretches to 100,000 astronomical units. Voyager is at 166. It has crossed roughly 0.17% of the distance to the outer edge of the Oort Cloud. The fastest object humanity has ever launched into interstellar space will take longer than all of recorded human history to exit the sun's gravitational domain. 30,000 years of silent drifting through the ghost shell, past trillions of frozen bodies it will never see, carrying a record it will never play, before it finally, quietly, slips free of the sun's grip and becomes a true interstellar traveler. That is how big the solar system is. Not 30 astronomical units, not 120. The sun holds everything in its grasp out to 100,000 astronomical units or more, and the fastest thing we have ever built, after nearly 50 years of flight, has covered less than 0.2% of that distance. We are in the courtyard of a continent, and the continent stretches to the horizon in every direction. But before we venture further outward, there is something back in the inner solar system that deserves our attention. Something beautiful, something temporary, something that is disappearing right now and will one day be gone forever. The rings of Saturn are dying, and we are lucky to be alive to see them. Chapter 8. Saturn is losing its rings. On March 23, 2025, Saturn's rings disappeared. Not permanently, not physically, they vanished from sight. Earth's orbital position aligned precisely with the plane of Saturn's rings, and for a brief period, we were looking at them edge-on. And because Saturn's rings, despite spanning roughly 280,000 kilometers across, are only about 10 to 30 meters thick in most places, viewing them from the edge is like looking at a sheet of paper from the far end of a football field. They become a razor-thin line, then nothing. This vanishing act happens roughly every 13 to 16 years, a consequence of Saturn's 26.7-degree axial tilt and its 29.4-year orbit around the Sun. It is not new. Galileo Galilei first observed it in 1612, when the strange appendages he had seen flanking Saturn through his early telescopes suddenly vanished. He was baffled. He had not yet understood that what he was seeing were rings. He thought Saturn had ears, and then one day the ears were gone. Historically, these ring plane crossings have been scientifically productive. 13 of Saturn's moons were discovered during crossings between 1655 and 1980, because with the overwhelming brightness of the rings removed, fainter objects near the planet became visible. The E-ring, Saturn's outermost major ring, was first spotted during a crossing in 1966. Every time the rings disappear, we learn something new about the system around them, but the 2025 disappearance carried a weight that previous crossings did not. Because we now know that Saturn's rings are not just temporarily invisible, they are permanently dying. NASA confirmed that Saturn is losing its rings through a process called ring rain. The rings are made primarily of particles of water ice, ranging in size from microscopic grains to boulders the size of houses. These particles are constantly being bombarded by ultraviolet radiation from the sun and by tiny high-speed impacts from micrometeoroids. When this happens, some of the ice particles become electrically charged. Once charged, they feel the pull of Saturn's magnetic field, which curves inward toward the planet at the ring's latitude. The charged particles spiral down along the magnetic field lines and fall into Saturn's upper atmosphere, where they vaporize. James O'Donoghue, a planetary scientist at NASA's Goddard Space Flight Center, calculated the rate. We estimate that this ring rain drains an amount of water products that could fill an Olympic-sized swimming pool from Saturn's rings in half an hour. Half an hour. Every 30 minutes, enough water to fill a competition pool is raining down from the rings into the planet's atmosphere, and it never stops. Adding to the ring rain, data from the Cassini spacecraft's grand finale in September of 2017, when Cassini dove between the rings and the planet's cloud tops before deliberately plunging into Saturn's atmosphere, revealed an additional flow of material falling directly from the innermost rings into the planet's equator. When you combine the ring rain with this equatorial infall, the rings have less than 100 million years to live, possibly as few as 100 million, possibly as many as 300 million. Either way, on a cosmic timescale, they are already halfway gone. And here is what makes that timeline even more striking. The rings may not be ancient at all. Analysis of Cassini data suggests that Saturn's rings may have formed only about 400 million years ago. If that is correct, we are witnessing the rings roughly in the middle of their existence. They were not here when the dinosaurs first appeared. They may not be here when whatever comes after us looks up at the sky. We are lucky. We exist during the brief cosmic window when Saturn wears its crown. Other gas giants may have once had similar ring systems. Jupiter, Uranus, and Neptune all have thin, faint rings today, barely visible even to spacecraft cameras. Some scientists have speculated that these planets once had rings as spectacular as Saturn's, rings that have since eroded away through the same processes that are now draining Saturn's. If so, Saturn's rings are not the norm. They are the exception, a temporary display, a cosmic fireworks show that happened to be running when we evolved the eyes to see it. Saturn itself is a world of staggering scale. It orbits the Sun at 9.5 astronomical units, roughly 1.4 billion kilometers away. Light takes about 80 minutes to reach it. A spacecraft takes 6 to 7 years. Saturn is 764 times the volume of Earth. You could fit the entire Earth inside Saturn's hexagonal polar storm, a persistent six-sided jet stream at the planet's north pole that has no equivalent anywhere else in the solar system. Saturn's moon, Titan, the only moon with a thick atmosphere, is larger than the planet Mercury. And Enceladus, tiny Enceladus with its water geysers, orbits within the E-ring that its own eruptions help to feed. The Cassini mission, which operated for 20 years, from 1997 to 2017, spent 13 of those years orbiting Saturn. Its final dive into the planet's atmosphere in September of 2017 was one of the most dramatic moments in the history of space exploration. The spacecraft was deliberately destroyed to prevent any possibility that it might one day crash into Enceladus and contaminate its ocean with Earth microbes. We killed the spacecraft to protect the possibility of alien life. That is either the most noble or the most absurd act in the history of exploration. Perhaps it is both. Saturn sits at 9.5 times Earth's distance from the Sun. But the solar system does not merely double from here, it explodes. Uranus is at 19.2 astronomical units, Neptune at 30. And these ice giants, the most distant planets, are the least understood worlds in our solar system. Only one spacecraft has ever visited them. Only one in the entire history of spaceflight. And that spacecraft is the same one that is now dying in interstellar space, its golden record drifting through a silence that will last longer than the sun. Chapter 9. The Forgotten Giants. Uranus rotates on its side. Its axial tilt is 97.8 degrees, meaning it essentially rolls around its orbit like a ball rolling along a floor while the other planets spin like tops. Something hit Uranus early in the solar system's history, something enormous, an impactor perhaps the size of Earth, and knocked it over. The collision was so violent that it permanently reoriented the planet. Every season on Uranus is an extreme. For roughly 21 years, one pole faces the sun in continuous daylight, while the other sits in continuous darkness. Then the planet rolls further along its orbit, and the poles switch. An entire hemisphere goes from decades of light to decades of night. Uranus orbits the sun at 19.2 astronomical units. Light takes approximately 2 hours and 40 minutes to reach it. And here is the fact that should embarrass every space agency on the planet. Voyager 2 is the only spacecraft that has ever visited Uranus. It flew by on January 24th, 1986. The encounter lasted roughly 5.5 hours of close observation. That is it. Everything we know about Uranus from direct exploration comes from 5.5 hours of data collected 40 years ago by a spacecraft that was not even designed to study it. Voyager 2 was built for Jupiter and Saturn. The Uranus flyby was an afterthought, made possible by a once-in-176-year alignment of the outer planets. In those few hours, Voyager 2 discovered 10 new moons, bringing the known total to 15. Today, we know of 27. It photographed Miranda, the innermost of the major moons, and revealed one of the strangest surfaces in the solar system. Miranda looks like it was assembled from mismatched pieces. Enormous cliffs, some of the tallest in the solar system. Grooved terrain sitting next to smooth plains, sitting next to ancient cratered regions. It looks like a world that was shattered and reassembled, or a world whose geological engine went haywire. We do not understand Miranda. We have 5 hours of data and a lifetime of questions. Some researchers now believe that another of Uranus's moons, Ariel, may harbor a subsurface ocean. Faint geological features suggest relatively recent activity on its surface, but without a dedicated mission, this remains speculation. Based on 40-year-old flyby images, Neptune is even farther. 30 astronomical units from the Sun. Light takes 4.2 hours to reach it. Voyager 2 arrived on August 25, 1989. Again, the only visit. Neptune revealed itself as a world of violent weather. The fastest winds in the solar system blow on Neptune, reaching speeds of 2,100 kilometers per hour. During the flyby, Voyager 2 observed the Great Dark Spot, a storm system the size of Earth swirling in Neptune's blue atmosphere. When the Hubble Space Telescope looked at Neptune years later, the Great Dark Spot was gone. It had dissipated. New storms had formed in its place. Neptune's atmosphere is a constantly churning engine of methane and hydrogen, driven by internal heat that the planet somehow generates, despite receiving almost no warmth from the sun. And then there is Triton, Neptune's largest moon. Triton orbits Neptune backwards. Every other large moon in the solar system orbits its planet in the same direction the planet rotates. Triton does the opposite. This retrograde orbit is powerful evidence that Triton is not native to Neptune. It is almost certainly a captured Kuiper Belt object, a world that was drifting through the outer solar system and was snared by Neptune's gravity at some point in the deep past. The capture process would have been violent, involving tidal heating that may have melted Triton's interior entirely. Voyager 2 observed nitrogen geysers erupting from Triton's surface, dark plumes rising 8 kilometers into the thin atmosphere before being sheared sideways by winds. Triton's surface temperature was measured at -235 degrees Celsius, making it one of the coldest surfaces ever recorded. And yet there are geysers. Something is generating enough energy beneath that frozen surface to produce eruptions. Some scientists believe Triton may have a subsurface ocean, yet another hidden sea in the outer solar system, yet another place where life might theoretically exist in the darkness. And we have no plans to go back. Not to Uranus, not to Neptune, not to Triton. The 2023 through 2032 Planetary Science Decadal Survey, the document that sets priorities for NASA's planetary exploration program, ranked a Uranus orbiter and probe as the #1 flagship mission priority. Number 1. The scientific community looked at all the places in the solar system we could go and said Uranus should be first. The ice giants are the most common type of planet in the galaxy. Surveys of exoplanets around other stars have revealed that planets similar in size and composition to Uranus and Neptune are far more numerous than gas giants like Jupiter and Saturn, and far more numerous than rocky planets like Earth. Understanding ice giants is not just about understanding our own solar system. It is about understanding most of the planets in the universe. And we have barely looked at the two in our own backyard. No mission has been funded. No mission has been launched. We know more about Jupiter's moons than we do about 2 entire planets in our own solar system. The ice giants are the forgotten worlds, and unless something changes, they will remain forgotten for decades to come. Beyond Neptune, beyond the Kuiper Belt, beyond even the extended belt that New Horizons discovered, the solar system becomes something else entirely. It stops being a collection of orbiting bodies and becomes a question of influence. How far does the sun's gravity reach? How far does its light matter? And what is it like out there, at the edge of everything, where the sun is just another star and the darkness is total? To understand that, we need to talk about light and time and the speed at which information itself decays across the solar system. Chapter 10. The Speed of Loneliness. Let us talk about light. Light is the fastest thing in the universe. Nothing with mass can travel faster. It moves at roughly 300,000 kilometers per second. In the time it takes you to blink, light has traveled from New York to Los Angeles and back 40 times. Light is instantaneous by every human standard of measurement. And yet in the solar system, light is slow. From Earth to the Moon, light takes 1.3 seconds. That is a conversation with a barely noticeable pause. From Earth to Mars, the delay stretches to between 3 and 22 minutes, depending on orbital positions. That is not a conversation anymore. That is a monologue followed by a long silence, followed by a reply that might not address what you actually said, because the situation changed 15 minutes ago. From Earth to Jupiter, light takes 33 to 54 minutes. From Earth to Saturn, 68 to 84 minutes. From Earth to Neptune, roughly 4.2 hours. From Earth to Voyager 1, the signal takes over 23 hours. Nearly a full day. If you screamed for help from the distance of Voyager 1, the fastest possible response, traveling at the absolute maximum speed allowed by the laws of physics, would take 2 days to arrive. 2 days of silence. 2 days of waiting. 2 days alone. Every meter farther from the sun, communication becomes harder, lonelier, more delayed. The solar system enforces isolation through physics. There is no technology that can overcome this. No antenna, no amplifier, no quantum trick. The speed of light is a wall, and the solar system is built on scales that make that wall feel like a prison. Now let us talk about travel. The Parker Solar Probe, at its closest approach to the sun, reaches speeds of 635,000 kilometers per hour. It is by far the fastest human-made object when measured near the sun. At that speed, you could reach Mercury in about 5 minutes, Venus in about 17 minutes, Mars in roughly 3.5 days, Jupiter in about 37 days. Neptune in about 240 days. But the Oort Cloud begins at 2,000 astronomical units. At Parker Solar Probe speeds, the inner edge of the Oort Cloud is roughly 13 years away. The outer edge, at 100,000 astronomical units, would take approximately 1,100 years. Over a millennium of travel, at the fastest speed humanity has ever achieved. No existing or proposed propulsion technology can cross the solar system in a human lifetime if the destination is the Oort Cloud. NASA has studied a concept called the interstellar probe, a mission designed to reach 1,000 astronomical units within 50 years, using a close solar flyby for a gravity assist. 1,000 astronomical units in 50 years. That is an impressive number, and it would still leave the spacecraft 99,000 astronomical units short of the outer Oort Cloud. The probe would reach the inner Oort Cloud. It would sample the environment there. It would send data back. But it would not cross the solar system, not by the Oort Cloud definition, not by a long way. Consider what this means for human exploration. Everything humanity has ever visited, every planet, every moon, every asteroid, every comet, exists within the innermost fraction of the solar system. The farthest flyby we have ever conducted, New Horizons at Arakoth, took place at 44.6 astronomical units. If the solar system extends to 200,000 astronomical units, then we have explored roughly 0.02% of it, 0.02%. We have explored less than 1/50th of 1% of our own solar system. We live in the courtyard of a continent, and we have not yet reached the garden wall. Everything beyond the garden wall, the Oort Cloud, the interstellar boundary, the true outer edge, remains as unknown as the deep ocean was to the first humans who walked along a beach and wondered what lay beyond the horizon. And the isolation is not just spatial, it is temporal. A mission to the outer Oort Cloud, even at speeds far beyond anything we can currently achieve, would take centuries. The engineers who designed it would be dead before it reached its destination. The civilization that launched it might not exist when the data came back. The solar system's scale does not just challenge our technology, it challenges our mortality. It challenges the continuity of our species. It forces us to ask whether human civilization can maintain purpose and coherence across timescales of centuries and millennia, because that is what exploring the full extent of our own solar system would require. The solar system is not a neighborhood. It is a continent, and we have explored a single city block. The rest is dark, cold, empty, and unimaginably far away. And every direction you look, the emptiness goes on and on, interrupted only by tiny frozen bodies drifting through a silence so deep that sound itself is a meaningless concept. But here is what makes the solar system's scale truly terrifying. It is not just that it is big. It is that it is temporary. Everything we have discussed tonight, the planets, the moons, the rings of Saturn, the Kuiper Belt, the Oort Cloud, all of it exists because of one object, the sun. And the sun is dying. Not tomorrow, not in 1,000 years, but it is dying. And when it goes, it will take everything with it. Chapter 11. The sun will eat the earth. The sun is a middle-aged star. It formed roughly 4.6 billion years ago from a collapsing cloud of hydrogen and helium. It has been burning hydrogen in its core through nuclear fusion ever since, converting 620 million metric tons of hydrogen into helium every second. At that rate, you might think the sun would run out of fuel quickly. But the sun is enormous. It contains 99.86% of all the mass in the solar system. Everything else, all the planets, all the moons, all the asteroids, all the comets, the entire Kuiper Belt, the entire Oort Cloud, together make up 0.14%. The Sun is not part of the solar system. The Sun is the solar system. Everything else is debris. But even the Sun has limits. In roughly 5 billion years, it will exhaust the hydrogen fuel in its core. When that happens, the core will contract under its own gravity, heating up as it compresses. The increased temperature will ignite hydrogen fusion in a shell around the core, pouring energy into the Sun's outer layers. Those layers will respond by expanding dramatically. The Sun will swell from its current size to roughly 256 times its current radius. It will become a red giant. Mercury will be consumed. The expanding Sun will engulf it entirely, vaporizing the small rocky world into plasma. Venus will follow. The Sun's atmosphere will extend beyond Venus's current orbit, and the planet will spiral inward and be destroyed. And Earth. Earth sits in the ambiguous zone. The Sun's expansion will extend to near Earth's current orbital distance. Some models suggest that as the Sun loses mass during its red giant phase, Earth's orbit will expand outward, keeping it just ahead of the advancing surface. Other models suggest that atmospheric drag from the Sun's tenuous outer envelope will overcome any orbital expansion, causing Earth to spiral inward and be consumed. Dimitri Veras of the University of Warwick, one of the lead researchers on the dynamics of dying stellar systems, has said he is confident that the Sun will swallow Mercury and Venus, and not Mars. But the fate of the Earth, which resides in between, is less clear. The honest answer is that we do not know if Earth will survive the Sun's death. It probably will not. But the margin is close enough that scientists are still arguing about it. And this is not just theoretical. We have watched it happen. In 2023, astronomers using the Gemini South Telescope and the Zwicky Transient Facility observed for the first time in history a dying star in the act of engulfing a planet. The event, designated ZTF SLRN 2020, produced a roughly 100-day optical flare as a Jupiter-sized planet spiraled into its host star. The star briefly brightened, then returned to normal. The planet was gone, vaporized, absorbed. Kishalay Day, the MIT researcher who led the study, stated the conclusion bluntly. This is the future of our solar system. In 2025, Stephen Kane of UC Riverside modeled the system Rho Coronae Borealis, a nearby star similar to the Sun that is nearing its red giant phase. It has 4 known planets. Kane's analysis showed that the 3 inner planets will be consumed when the star expands. The 4th, farther out, will survive, but on a dramatically altered orbit. After the red giant phase, the Sun will shed its outer layers, expelling them into space as a glowing planetary nebula. What remains will be the core, a dense ball roughly the size of Earth, but containing about 60% of the Sun's original mass. This remnant is called a white dwarf. It will glow dimly, cooling slowly over billions of years, radiating the last of its heat into the void. The outer planets will survive the transition, but their orbits will roughly double in size as the Sun loses mass. Neptune will drift to roughly 60 astronomical units. Jupiter and Saturn will move outward as well. The solar system will become a wider, darker, colder place, lit only by the fading ember of a dead star. But here is a detail that emerged from research in 2025 that adds an extraordinary coda to this story. A team at Cornell University, working with the Carl Sagan Institute, modeled what would happen to Europa during the red giant phase. Right now, Europa's ocean is locked beneath 15 to 25 kilometers of ice, kept frozen by the feeble light of a sun that is nearly 800 million kilometers away. But when the Sun becomes a red giant, its luminosity will increase enormously. The extra energy will melt Europa's ice. For a period of up to 200 million years, Europa could have a warm liquid ocean on its surface, open to space, bathed in light. 200 million years is long enough for life to emerge. It is longer than the entire age of the dinosaurs. The last habitable world in the solar system might not be Earth. It might be a moon of Jupiter, briefly warmed by the dying light of an expanding star, hosting an ocean that exists for a geological blink before the sun collapses into a white dwarf and the cold returns forever. Long before the sun dies, long before the red giant phase, something else will happen. The sun is gradually getting brighter. It increases in luminosity by roughly 1% every 100 million years. Within the next billion years, the increased solar output will push Earth's surface temperature beyond the point where liquid water can exist. The oceans will evaporate. The atmosphere will become a thick steam greenhouse. Life on Earth will end, not from the sun's death, but from its slow brightening. We are not at the beginning of Earth's habitable period. We are closer to the end. Life has existed on Earth for roughly 3.8 billion years. It may have only 1 billion years left. We are in the final quarter. And that raises a question that the size of the solar system makes almost painful to ask. If life needs to leave Earth eventually, can it actually go anywhere? Chapter 12. Can we ever leave? The nearest star to the Sun is Proxima Centauri. It is a small red dwarf in the Alpha Centauri system, 4.24 light-years away. That sounds like a number. Let us make it feel like a distance. At the speed Voyager 1 is traveling, roughly 61,200 kilometers per hour, the trip to Proxima Centauri would take approximately 73,000 years. At the speed of New Horizons, about 58,000 kilometers per hour, it would take roughly 78,000 years. At the top speed of the Parker Solar Probe, 635,000 kilometers per hour, the fastest any human-made object has ever traveled, it would still take approximately 6,600 years. No existing propulsion technology can deliver a crewed spacecraft to the nearest star within a human lifetime. Not chemical rockets, not ion drives, not nuclear thermal propulsion. The distances between stars are not merely large, they are a different category of large. They are large in the way that the ocean is a different category of large from a swimming pool. You cannot cross the ocean by swimming faster. You need a fundamentally different approach. Several fundamentally different approaches have been proposed. None of them exist yet. The most ambitious near-term concept is Breakthrough Starshot, funded in part by the late physicist and entrepreneur Yuri Milner. The idea is to build tiny spacecraft, each weighing only a few grams, equipped with light sails several meters across. A massive ground-based laser array with a total power output of roughly 100 gigawatts would fire a concentrated beam at the sail, accelerating the probe to roughly 20% the speed of light. At that velocity, the craft would reach Proxima Centauri in approximately 20 years. Data from the flyby would be transmitted back to Earth and would arrive 4.24 years later. The concept is elegant. The physics are sound in principle, but the engineering challenges are enormous. The laser array does not exist. The sail material, which must be nearly perfectly reflective and incredibly thin, has not been developed. The probes must survive acceleration forces and 20 years of interstellar travel without degrading. There is no way to slow down. The probes would streak through the Proxima Centauri system at 20% the speed of light, gathering data for a few frantic seconds during the flyby, and then continue into deep space forever. And the payload capacity is essentially zero, a few grams, enough for a camera chip, a communications laser, and basic sensors. Not enough for a person, not enough for a lab, not enough for anything resembling exploration as we understand it. Nuclear pulse propulsion has been proposed in various forms since the 1950s. Project Orion, conceived at General Atomics, envisioned a spacecraft propelled by detonating nuclear bombs behind it. Each detonation would push against a massive steel plate at the rear of the ship, gradually accelerating it to perhaps 5% the speed of light. At that speed, the journey to Proxima Centauri would take roughly 85 years, still longer than a human lifetime, but conceivably within the span of a multi-generational crew. The concept was seriously studied by the United States military and by NASA. It was abandoned, in part because the Partial Test Ban Treaty of 1963 prohibited nuclear detonations in space, and in part because the engineering challenges were and remain staggering. Then there are generation ships. The idea is simple in concept and mind-breaking in execution. Build a spacecraft large enough to sustain a human population for centuries. Launch it toward another star. The people who arrive at the destination will not be the people who launched. They will be the descendants, born and raised on the ship, knowing no world but the vessel that carries them. The engineering requirements are almost inconceivable. You would need a self-sustaining ecosystem capable of recycling air, water, and food indefinitely. You would need a governance system that remains functional across dozens of generations. You would need genetic diversity sufficient to maintain a healthy population over centuries. You would need propulsion that can sustain acceleration for years. No such technology exists. No such ecosystem has ever been created. We cannot even build a fully self-sustaining habitat on Earth, let alone one that must function in the vacuum of space for hundreds of years. The solar system's scale reveals an uncomfortable truth. Even leaving the solar system, defined as reaching the outer Oort Cloud, would take tens of thousands of years with current technology. Reaching another star would take longer still. Interstellar travel is not merely an engineering challenge. It is a challenge to the fundamental physics of propulsion and the biological limits of human lifespans. We may be permanently confined to the inner solar system, the first 50 astronomical units, for centuries or millennia to come. And even within that space, we have explored almost nothing. But maybe the question is not whether we can leave. Maybe the question is whether we should be looking at what we already have differently. Because the solar system, this vast, mostly empty, apparently hostile place, contains something extraordinary, something we are only now beginning to appreciate. It contains water everywhere, in places we never expected. And where there is water, there might be life. Not life we would recognize, not life that looks like us, but chemistry, doing what chemistry does when conditions are right, organizing itself into something that persists, something that grows, something that might. In the darkness beneath the ice of a frozen moon, be quietly, patiently, alive. Chapter 13. Water everywhere, life nowhere yet. 30 years ago, the conventional wisdom was straightforward. Liquid water in the solar system existed in one place, Earth. The habitable zone, the narrow band, around a star where temperatures allow liquid water on a planet's surface, was a thin ring. Venus was too close and too hot. Mars was too far and too cold. Earth was just right. Everything beyond the asteroid belt was frozen solid. End of story. That story is dead. The solar system is drowning in water. We just did not know where to look. Europa, as we discussed, harbors an ocean containing 2 to 3 times the volume of all Earth's oceans. Beneath 15 to 25 kilometers of ice, salt water sloshes in the dark, kept liquid by tidal heating from Jupiter's enormous gravity. The ocean has been there for billions of years. It is vast, deep, and completely hidden from the sun. Enceladus, Saturn's tiny moon, punches above its weight. The Cassini spacecraft flew through geysers erupting from its south pole and found water, sodium chloride, silica nanoparticles, molecular hydrogen, carbon dioxide, methane, and complex organic molecules with masses above 200 atomic mass units. Everything a microbe would need. The geysers are shooting the ocean into space, making Enceladus the only world in the solar system where you can sample the ocean without even landing. Just fly through the plumes and open your mouth. Ganymede, Jupiter's largest moon and the largest moon in the solar system, is believed to have a subsurface ocean sandwiched between layers of ice. Callisto, another of Jupiter's Galilean moons, may also harbor liquid water beneath its ancient cratered surface. Titan, despite the revised understanding of its interior as more slush than sea, may still contain pockets of liquid water mixed with ammonia deep below its methane-soaked surface. And then there are the surprises. Triton, Neptune's captured moon, may have a subsurface ocean. Pluto, the former planet at the edge of the Kuiper Belt, shows evidence of a subsurface ocean of slushy ammonia, rich water beneath its nitrogen ice plains. Even Ceres, the largest object in the asteroid belt, showed evidence of briny liquid reaching its surface when the Dawn spacecraft studied it. The habitable zone concept has been shattered. Liquid water does not require proximity to a star. It requires a heat source, and tidal forces from giant planets can provide that heat even in the frozen darkness of the outer solar system. The old textbook picture of one narrow ring of possibility has been replaced by a solar system peppered with hidden oceans, from the asteroid belt to the Kuiper Belt. And yet, we have not found life. Not anywhere beyond Earth. Not microbes, not fossils, not chemical signatures that unambiguously indicate biology. Decades of Mars exploration have yielded nothing definitive. The Viking landers in 1976 performed experiments that produced results, still debated nearly 50 years later. Curiosity and Perseverance have found organic molecules on Mars, but organic molecules are not life. They are ingredients. You can find organic molecules on comets and asteroids and in interstellar gas clouds. Their presence is necessary for life, but not sufficient proof of it. The Europa seafloor study, published in January of 2026 by Paul Byrne and colleagues, cast doubt on one of the key mechanisms scientists had hoped would support life on Europa, but it did not close the door. The sinking ice mechanism discovered in that same month offered a new pathway for nutrients to reach the ocean. The question is not settled. It is barely begun. Within the next decade, 3 major missions will explore ocean worlds in the outer solar system. Europa Clipper, arriving at Jupiter in 2030, will make 49 flybys of Europa, mapping its ice, analyzing its chemistry, searching for signs of habitability. JUICE, the European Space Agency's Jupiter Icy Moons Explorer, will arrive at Jupiter in 2031 and eventually enter orbit around Ganymede, the first spacecraft ever to orbit a moon of another planet. Dragonfly will arrive at Titan in 2034, flying through its thick atmosphere, sampling its surface chemistry, listening to its interior. None of these missions are designed to detect life directly. They are designed to assess habitability, to determine whether the conditions for life exist. But if they find the right chemistry in the right conditions, the right mix of water, energy, and organic molecules in an environment that has been stable for billions of years, they will change the question from "Is there life?" to "How could there not be?" Paul Byrne, despite his own study casting doubt on Europa's seafloor, expressed a sentiment that captures the spirit of this search. "I am not upset if we do not find life on this particular moon. I am confident that there is life out there somewhere, even if it is 100 light-years away. That is why we explore, to see what is out there. The solar system is the only laboratory we have. Every answer about life in the universe starts here. If we find life on Europa or Enceladus, life that arose independently from life on Earth, it would mean that biology is not a freak accident. It would mean that wherever conditions are right, life happens. And given the trillions of planets in the galaxy, many of them orbiting in the habitable zones of their stars, many of them with liquid water, that would mean the universe is teeming with life. Everywhere. If we search and find nothing, that tells us something too. It tells us that the conditions for life are not sufficient, that something else is needed, something rare, something we do not yet understand. And that would make Earth and the life it carries even more precious than we already know it to be. We have traveled from the surface of Earth to the edge of the Oort Cloud tonight. We have measured the solar system at every scale, from the 30-meter thickness of Saturn's rings to the 3-light-year diameter of the Sun's gravitational domain. We have watched our spacecraft die in the dark and our planet's future written in the death of stars. There is one more thing to see, one more perspective, the view from outside. What does our solar system look like from the stars? And what does our silence say about us? Chapter 14. The view from outside. Let us leave. Let us go to Proxima Centauri, 4.24 light-years away, and look back at our solar system. What would we see? We would see a star. A moderately bright yellow star, unremarkable among the thousands visible in the night sky of whatever world orbits Proxima. Not the brightest, not the dimmest, just another point of light. The planets would be invisible. Even with a telescope as powerful as the James Webb Space Telescope, the planets of our solar system would be lost in the glare of the sun. Jupiter, the largest of them, would be a speck 1,000 times fainter than the star itself, drowning in the diffraction pattern of the sun's light. Our radio signals have been traveling outward at the speed of light for roughly 125 years. Since the earliest radio experiments at the turn of the 20th century, at the speed of light, those signals have reached a sphere approximately 125 light-years in radius. That sounds impressive until you realize that the Milky Way galaxy is roughly 100,000 light-years across. Our radio bubble, the sum total of every broadcast, every signal, every transmission humanity has ever made, occupies a sphere smaller than 0.1% of the galaxy. And the signals at the edge of that sphere are so faint, so diluted by the inverse square law of electromagnetic radiation, that they are effectively undetectable by any technology remotely comparable to our own. From the outside, the solar system is invisible. A single ordinary star with no detectable companions. No sign of civilization. No sign of water. No sign of anything remarkable at all. If an alien astronomer on a planet orbiting Proxima Centauri scanned our star with a telescope equivalent to the James Webb, they might, with extreme luck and precise timing, detect a slight dimming as Earth transited the face of the Sun. They might infer the existence of a rocky planet in the habitable zone. They would know nothing else about us, not that the planet has liquid water, not that it supports life, not that a species on its surface built spacecraft and sent them into the void. We are invisible, and that is perhaps the most humbling thing the size of the solar system can teach us. On February 14th, 1990, the Voyager 1 spacecraft turned its camera backward and took a photograph of Earth from a distance of roughly 6 billion kilometers. Earth appeared as a sub-pixel pale blue dot caught in a scattered beam of sunlight. Carl Sagan wrote about that image with words that have become perhaps the most famous passage in the history of science communication. He spoke of every human who ever lived, every king and peasant, every saint and sinner, every creator and destroyer, on that mote of dust suspended in a sunbeam. But here is the thing that is rarely mentioned. That photograph was taken from barely outside the planetary solar system, roughly 40 astronomical units. Not even at the Kuiper Belt. Not even at the heliopause. A trivial distance by the standards of what we have discussed tonight. If Voyager took the same photograph from the Oort Cloud, Earth would be entirely invisible. The Sun itself would be a faint star. Everything we are, everything we have built, everything we know would be lost in the blackness, indistinguishable from nothing. And yet, the solar system is not nothing. It is unimaginably, paralyzingly vast. It contains more water than we knew, more structure than we expected, more mystery than we can currently solve. It contains hidden oceans beneath moons of ice. It contains a ghost shell of trillions of frozen objects that we have never seen. It contains a dying pair of spacecraft carrying golden records into an eternity of silence. It contains rings of ice that are slowly raining down onto a gas giant, disappearing forever in the geologically brief window when we happen to exist. It contains 2 entire planets that we have visited only once, for a few hours, with a single spacecraft, and then never returned to. It is also the only home we will have for a very, very long time. The distances to the stars make that clear. The distances within the solar system make it clear too. We have barely explored our own backyard. The inner 50 astronomical units are the only territory we have ever touched. And even within that narrow band, our knowledge is riddled with gaps and questions and things we thought we knew, but turned out to be wrong. But we looked. That is the thing. We looked. We built Voyager and sent it outward. We built IMAP and launched it to map the wall between us and the galaxy. We are sending Europa Clipper to search for life in an ocean we have never seen. We measured the Oort Cloud without ever photographing a single object in it. We watched Saturn's rings disappear and calculated when they will be gone forever. We sent a student-built dust counter to the edge of the Kuiper Belt and discovered that the solar system is larger than anyone thought. We are a species that lives on a speck, orbiting an ordinary star, in a solar system so large that the fastest thing we have ever built will take 30,000 years to cross it. We live for roughly 80 years. The sun has been burning for 4.6 billion. The Oort Cloud stretches 3 light years across. And we, tiny, brief, fragile, confined to a paper-thin layer of atmosphere on a world barely visible from the next planet over, are the part of the solar system that knows how big it is. That knowing is not nothing. In a solar system defined by emptiness, by silence, by distances so vast that they mock every vehicle we have ever built and every dream of escape we have ever entertained, the fact that a species of primates on the 3rd rock from the sun figured out the size of the place, measured it, mapped it, named its boundaries, calculated its future, mourned its mortality, and then went back to work the next morning, that is not nothing. That may be the largest thing in the solar system. The solar system is vast and mostly empty and mostly dark, but it contains us. And we, for all our limitations, are the part of it that looked up and asked, how big is this place? And then, astonishingly, found the answer. And kept looking anyway. If you enjoyed this deep journey into the true scale of our solar system, please like this video and subscribe to the channel. Your support makes these detailed investigations possible. Tell me in the comments which fact about the solar system's size surprised you the most, and where in the solar system would you most want to explore if distance were no object. These are not just questions for scientists, they are questions for all of us, because the solar system is our home, and we have barely begun to know it. Thank you for watching. I will see you in the next investigation.